Welcome everyone. We are Group 7 and our presentation is titled Aspen HYSYS Applications in Petrochemical Productions. Our presentation will discuss two research articles that both utilizes Aspen HYSYS and MATLAB in simulating various plant conditions and ultimately generating significant findings. The first research article is The Optimization of Linear Alkyl Benzene Yield Through Modeling and Simulation by Usman Ali, Muhammad Zafar, Ashfaq Ahmed, and et al.
Demand for consumer products such as detergents, soap, shampoos, cosmetics, and emulsifiers continue to rise due to the increase in population. As a result, the production of linear alkylbenzene, or LAB, which is the key ingredient in the production of these products, has increased. Along with the swift demand for the said chemical product, most industries began using LAB to replace branched alkylbenzene due to the environmental issues. In order to maximize profit, process engineers need to increase yield and reduce operating and investment costs, which is where modeling and simulation play a very crucial role. Listed below are the problems encountered in lab production. First is the creation of undesirable olefins. Second is the instability of thermodynamic variables such as temperature, pressure, and flow rate. Some research works attempted to maximize the yield of lab by only simulating a single unit or a single variable. Thus, the objective of this study is to simultaneously simulate the lab plant in order to achieve the maximum yield of lab. Specifically, the research article aims to contribute towards the improving of yield of lab plant of Kaduna Refining and Petrochemical Company by utilizing Aspen and MATLAB to model, simulate, and optimize the plant. For the optimization of the plant, the research article used the response surface method, which was carried out using the Design Expert version 13, and the particle swarm method, which was accomplished in MATLAB.
Hello, this is Czarielle, PENEQUITO, and I'm here to discuss the materials and methods used for the optimizations of alkyl benzene yield. So the applications used for the data collection were as follows: Aspen HYSYS version 11, Design Expert version 13, MATLAB 2018 B software. Aspen HYSYS version 11 is developed to perform mathematical and chemical models and fully calculate engineering calculations such as mass and energy balance, equilibrium, heat and mass transfers, and more. Similarly, MATLAB is a desktop application tuned to analyze and design processes using programming languages that express matrices and arrays. Design Expert is a statistical software for conducting experiments that require a thorough examination of relevant information and variables as well as experiment-related elements. So the process data were collected from the linear alkyl benzene plant log sheet of flow data sheet of lab production process or KRPC. In order to replicate the operation of the Pacol and Dettol units of the production system, feed data such as mass flow rate, temperature, pressure, and more were used as equipment operating parameters. For the methods, these research mainly use three methods: Aspen for the modeling and simulation procedure, numerical method of RSM, and particle swarm. Aspen was used to model Pacol and Dettol units of the lab production plant, as shown by the black flow diagram, to test the parameters obtained from KRPC. The steps were as follows: component database, thermodynamic model solver, flowsheet builder, unit operation block builder, data output generator, and flowsheet solver. How Aspen was used in this experiment, the simulation steps, and its technical aspects will be further expounded later. The other methods used the applications Design Expert and MATLAB to optimize the developed linear model. The Design Expert was used to optimize response surface methodology, or RSM. The RSM is a useful tool to design systems with no mechanistic information. As a start, the researcher carried out a set of 30 experimental trials using the central composite design of the RSM. Meanwhile, MATLAB was used to accomplish particle swarm, a method used for optimization and comparison purposes.
Now, for the second research article, the optimization of linear alkyl benzene yield through modeling and simulation. Model and simulation of the process systems is an important tool in reducing risk of operation, investment, and operating costs due to system failures, thereby improving the performance of the process systems. Prior to modeling and simulation of LAB plant of the Kaduna Refining and Petrochemical Company, or the KRPC, existing data were collected from the flow sheet and operating manuals of the LAB plant of the company. The data were then used for the simulation, and as can be seen in Table A, it shows the results of the simulation of the LAB plant testing different thermodynamic models. The thermodynamic models used was the Peng-Robinson model, Wilson model, the non-random, two liquids ideal models, the unique QAC, and the Suave-Frederick-Kwong thermodynamic model. And it can be observed that the Peng-Robinson model is the only one that has a positive difference in terms of the simulation yield compared to the actual plant yield. Because this as a fluid package resulted to 3,800 kilograms of LAB per hour, which was observed to be higher than the LAB yield of the plant, of the company plant, of 3,788 kilograms per hour as obtained from the datasheet. Comparing the plant yield to the yield obtained from the simulation using each of the fluid packages, it was obvious that only with Peng-Robinson that an improved yield was obtained with 0.316% increment, or in the table, 0.32% increment, or positive difference. And we can see in Table 9, the essential composite design matrix and obtained values of the response. These independent variables, the pack hole temperature, the pack hole pressure, the Detal temperature, and the Detal pressure, these values were obtained using the response surface models, or the response surface methodology. The paper did not actually, or the authors did not specify which software they used to generate these values, but it's most likely from MATLAB. So MATLAB has a syntax for RSM, which is RSM demo. It opens a group of 3 graphical user interfaces for interactively investigating response surface methodology, RSM, nonlinear fitting, and design of experiments. The interfaces allow you to collect and model data from a simulated chemical reaction. This is an example obtained from the MathWorks website, and its independent variables is the hydrogen, the normal pentane, and the isopentane, and the generated data is the reaction rate. It is very similar with the table from the research article, with the generated data being the simulation yield, or the response. Here we actually would input the data and then run this interface like application, and then in the research article they did a total of 30 runs, but this one they did 13 runs. And then we analyze, we plot, and then we click the do experiment, and the data will be automatically generated. So that is how these values came about. And by using the design matrix data given in Table 7 earlier, a model relating the LEB yield and the operating conditions of the pack hole and data reactors, which were the independent variables of the temperatures and pressures, developed. These were developed actually using this model given in equation 1. As you can see, here it is, and Table 7. And this equation was actually derived using this design matrix. This one, table 7. And then you can see here in table 10, when the results of the analysis of variance ANOVA for lab yield, we are also assuming that this was done in MATLAB because they did not also specify which application they used. And it's safe to assume too, because as you can see here, an example from the MathWorks website, they have the same generated values. This is the syntax. You will generate a matrix, and then the graph will then be automatically made. And then we have the p-value. And as it can be noticed from table 10, that the Paco temperature A and the delta temperature C were the significant in terms of the model, with p-value of 0.0179 and less than 0.001 respectively, which are less than 0.05, so they are considered statistically significant. You can actually see the generated graphs here for the Paco temperature, Paco pressure, the delta temperature, and delta pressure. And in the graphs for both the Paco and the delta temperature, actually, which were the said significant factors, they have actually almost all of them have positive slopes, but the rise in slope of these two graphs is more significant than compared to all of them, because you can see in for the Paco pressure and Paco pressure and the delta pressure, there are also positive slopes. They are increasing, but if we would extend the slope with a much more increasing pressure of the Paco and the delta reactors, it could actually result to a straight line that would not generate significant changes anymore. Thus, it would not yield more LAB compared to the graph of the Paco and the reactor temperatures. So we can say that the temperatures are the factors or the independent variables that affects the percentage yield of the LAB at the end of all of the processes. And the obtained R-squared value of the model was 0.7075, which means that the model was able to explain more than 70% of the variations in lab yield, which occurred as a result of the change in the value of the considered independent variables, which is the significant in terms of temperature. But also pressure can also contribute. All of them contribute, but temperature contributes much higher results.
The study found the following results from this simulation. For the thermodynamic model variation study, it has been found that the most efficient model is the Rasmussen's SRK, or Skill Rule Knowledge model. In this model, they have obtained 3,800 kg per hour yield of the LAB, while the least efficient model is the Peng-Robinson model, which garnered 3,666 kg per hour. More than proper selection of thermodynamic model, of course, process condition settings are optimized via particle swarm and RSM utilizing MATLAB. And results show that the RSM optimization generated optimal temperature and pressure for Paco. And this temperature is 457 degrees Celsius and the pressure is 2.32 kilogram per cubic centimeter gram. While for Detal, the temperature is 275.69 degrees Celsius and the pressure is 2.82 kilogram per cubic meter gram. And then the optimal yield obtained was 3,800.669 kilogram per hour of LAB, quite similar to the Rasmussen's SRK model. Moreover, the simulation for optimized condition resulted in 3,868 kilogram per hour of LAB, while particle swarm optimized plant yield by 1.85% at optimum operating conditions of temperature and pressure for Paco, which is equal to 500 degrees Celsius, and pressure of 3.5 kilogram per cubic centimeter gram, while the tal is 280 degrees Celsius and a pressure of 4.5 kilogram per cubic centimeter gram and has a yield of 3,862 kilogram per hour of LAB. From this solution, we can either conclude or we could either choose from these two variations because one the RSM optimization showed lower lower operating conditions, which means savings on energy. However, the yield is also low. This is in contrast to the particle swarm optimization yield, wherein there is higher yield, quite close to 3,800 to the actual yield. However, the energy utilization is quite high, a bit higher compared to the RSM optimization model. Ultimately, a model has been developed relating the operating conditions and lab yield with the R squared equaling to 0.7075, which indicated that the model was able to explain more than 70% of the variations in the lab yield result, which occurred because of the change in the independent variables. This only shows that this model is more than 70% reliable in proving that the yield obtained from this relation is quite true. So overall, we can say that the HYSYS and MATLAB are effective in achieving three things. One is that it is effective in simulating and optimizing the process, since we can see that it has optimized the energy efficiency, also the yield. Also, it has provided success in simulation, and we have proven this because the yield obtained is quite close to the 3,800 kilogram per hour actual yield of LAB using from the actual LPG recovery process. We have also modeled a relationship for the yield involving the independent parameters such as the pressure, temperature of PACOL, um, and that proved 70% reliability. Also, it has validated, as we have seen, there is we can see that the actual and then the actual yield and then the optimized yield are quite near.
The second research article is titled Techno-Commercial Analysis of LPG Recovery from Natural Gas Using Aspen HYSYS by Ahmed Mohamed Inua, Saidat Olanipekun Diwa, and Atuman Samaila Joel.
Energy resources are depleting rapidly due to increased globalization and urbanization. Liquefied petroleum gas, or LPG, an alternative, relatively clean, and supreme source of energy, is being used as a key component in the global energy supply. LPG, which is designated as butane and mere propane in an engineering context, is extracted from natural gas. The said gas is preferable due to its limited contents of sulfur while burning and because it gives no soot to the environment. With various alterations and proposals available in literature, the effect of cooling, disposition, and rerouting the process streams is seldom reported. In result, this research work is focused on the improvement in the yield of LPG production by increasing or altering the process of cooling or their orientation in the separation and hydration section of the natural gas processing plant. 3 cases are studied in this research work to increase LPG recovery from natural gas by analyzing their cost and process parameters. In case study 1, the feed is pre-cooled through cold box. The position of the chiller will be placed in the separation section in case study 2, while in case study 3, the position is in the dehydration section. The case studies and their variations will be further explored in the methodology. As this research work is based on modeling and simulation to improve the currently used recovery processes in the industrial sector of Pakistan, the aim of this research is to study the varying flowsheet alternatives and compare their performances. The evaluation of criteria will be the capacity of different products for their different alternatives, energy in terms of cold and hot utilities, and lastly, economic analysis.
Here we have the black flow diagram for the LPG production from natural gas as shown in the figure on the screen. It indicates that the LPG production from natural gas is composed of four subsections. Initially, the feed is treated, which is designated by feed separation and the dehydration section. Later, NGLs are recovered by using a refrigeration loop and a cold box. And then, LPG is recovered and is attained by the use of distillation columns. And these columns are indicated as NGL and LPG recovery sections. So getting into the PFD or the more detailed process of the of LPG recovery. So the feed treatment section consists of removal of heavier hydrocarbons and water from natural gas before its processing, and it consists of two subsections. The first one is a separation zone, and the second subsection is a dehydration zone. Then in the separation section, composition is analyzed, and to avoid moisture, saturator is installed to avoid further moisture buildup. And because of the sensitive nature of the material of construction of the downstream cold box, water is desired to be extracted in a three-phase separator. And for LPG recovery, greater pressure is recommended. Hence, pressure is set as high as 600 psig, and dry gas streams containing zero impurities is recommended in the process. Any type of free H2O is extracted from this stream, and this separator will remove higher hydrocarbons, mud, and water from the stream. And a stabilization unit is also installed to stabilize the condensate, and heavy liquids are removed from the stream and converted into fluid fuel. Next, the dehydration section further removes traces of water through the use of molecular sieves. In comparison with other dehydration techniques, molecular sieves have a relatively higher efficiency to extract maximum contents of water from the natural gas feed stream. And these sieve beds with tandem or parallel arrangement can be regenerated and reused by heating. So that's very efficient and sustainable. And in general, parallel orientation of two beds is recommended in LPG production. After that, the gas will be forwarded to the cryogenic section of the plant, in which maximum removal of liquid from gas is performed. And to obtain the cryogenic condition, a turbo expander is utilized to apply the chilling process. So the stream to be liquefied is passed through a multi-pass heat exchanger, aluminum alloy based with a plate and frame type arrangement. So the transfer of heat occurs between the mainstream of the process and then the downstream process, approaching from the low temperature absorber and LPG recovery unit. So the second cold box is also installed as a stand heat exchanger. So the turbo expander and lower temperature are utilized to extract the liquid from the core stream. The gas stream is expanded by the stated turbo exchanger, and ultimately a decrease in temperature of the stream is observed. The gradual processing of the gas stream results in a steady decrease of the higher hydrocarbons to produce refined LPG. Finally, LPG extraction is the closing and conclusive section of the stated scheme. And the ultimate amount of C3H8 and C4H10, named LPG, is recovered through this section. Distillation columns such as the debutanizer and the ethanizer will take out the required hydrocarbons completely.
Hello, I'm back again, but this time I'm going to discuss Aspen modeling used in LPG recovery. So it was mentioned before that Aspen is developed to perform mathematical and chemical models and fully calculate engineering calculations such as mass and energy balance, equilibrium, heat and mass transfers, and more. It is extensively utilized in the industry and academics and is often used for steady state and dynamic simulations. It addresses the problems that the first principle models cannot solve, and a first principle model reflects the physical laws and is often dependent on the relationships of a particular unit operation in a chemical process. So, how was Aspen used in this research? So the researchers used Aspen to make LPG recovery become more energy and economically efficient, and to obtain the maximum yield from natural gas with increased purity. They used Aspen to simulate a steady state, and it is divided into sections: the separation zone, the hydration zone, NGL extraction zone, and LPG recovery zone. And then it is integrated into the primary flow pattern. The produced result of the model is further utilized to calculate the physical, chemical, and overall energy of each auxiliary. The complete energy analysis performed on the liquefied petroleum gas recovery plant provided specific points of inefficiencies on the previous model, prompting the use of Penn-Robinson equation of state and base case steady-state model developed in Aspen.
Case Study 1. Cooling process is directly proportional to the recovery of LPG. The conversion into liquid form and production of LPG will be increased. Temperature of feed is decreased and separation is more perfect. Maximum liquid is extracted from stream through a separation process and due to its extraction from the stream, which leads to a low content on the downstream gas. And the feed stream is decreased from 140 Fahrenheit to 48 Fahrenheit, which is reasonable difference in temperature change. At low temperature, the effectiveness of absorption is enough to extract the moisturizing content, easily containing a low leading to better LPG recovery. Case Study 2. Change the chiller position from LPG extraction section to separation section. The temperature of the feed stream is lower than Case Study 1 is. It goes from 140 Fahrenheit from the base case to 17.7 Fahrenheit in Case Study 2. The major portion of water in separation section and heavy hydrocarbons are removed. Directly sent to the LPG unit without passing through the dehydration as well as NGL extraction sections favorable in terms of capital as well as operational cost. A decrease in size of equipment and cost results are obtained with this arrangement. Case Study 3. The position of the process equipment is changed in Case Study 3. The position of the chiller is moved from the NGL extraction zone to the dehydrating zone. Inlet gas entering the dehydrating zone is chilled by the change. The size of the bed is lower than the base case and other cases. Temperature decreased to about negative 9.2 Fahrenheit from 140 Fahrenheit. Molecular sieve volume is also decreased by decreasing the size of the bed. A lower volume of the molecular sieve will be required. Activity of the amount of molecular sieve in the base case will be greater for a long time than the present case. Economic analysis. There is no drift change in the operational cost for the base case and any alteration proposed in the base case. The capital cost of different case studies in Figure 9 shows a small increase of capital cost of about 2% in Case Study 1 in comparison to the cold box. A sharp decrease of nearly 18 and 22% lower size of absorption units. The decrease in temperature to an acceptable minimum level for maximum recovery of LPG, refrigeration process, and chilling process will have a greater effect on the overall capital cost. In Figure 10, Case Study 3 will have the least cost compared to the base case and Case Study 1 and 2.
The objective of this research study was to find the capability of investigating the liquefied petroleum gas recovery performance to make the process economical by saving the processing cost and energy. Various flow sheets alternatives were studied and comparisons were made of the performance of each of the case studies. The results were evaluated based on the capacity of different products for the different alternatives, energy in terms of cold and hot utilities, and economic analysis. Through Aspen HYSYS, a steady-state simulation model was prepared. The flow sheet was decentralized into 4 zones: the separation zone, the hydration zone, the NGL extraction zone, and the LPG recovery zone. The base case steady-state model, Peng-Robinson equation state, was used to conduct a complete energy analysis of the liquefied petroleum gas plant to find the specific points of the efficiency losses. Based on the exergy analysis made, the NGL recovery process through modeling and simulation in Aspen HYSYS indicated that most of the exergy destruction happens at the air cooler and the column present in the flow sheet. In case study 1, the natural gas is rerouted through the cold box 1. In case study 2, the chiller position is in the separation section while it is in the dehydration section for case study 3. It is observed that case study 3 is the optimized configuration in the context of the process and economic parameters when compared with all the other case studies. In case study 3, gas cooling is accomplished just after the separation and it is upstream of the dehydration section with optimized size specification of the molecular sieve dehydrator bed and low temperature absorber. Furthermore, the turbo expander and low temperature absorption configuration system produced greater recovery of liquefied petroleum gas. With the amount of 1,110 pounds per hour of LPG was obtained out of 5 million standard cubic feet per day of raw natural gas with a maximum purity of 99.9%.